All right, let's get right into it. Today, we're going to talk about a whole new way to build AI agents. We're moving past these super fragile, monolithic prompts and into a world where our agents are built on resilient, evolving, and totally auditable genomes. This right here is the big challenge, isn't it? It's the core tension every single one of us building AI products is dealing with. How do we move fast? How do we innovate? But at the same time, make sure our agents are safe, they're reliable, and they don't have these invisible risks that could just blow up on us later.
Well, a really interesting playbook for this exact problem is laid out in a new paper. It's called Genetic Prompt Engineering plus Context Engineering, a genome-style architecture for safe, self-evolving AI agents by Nir Cohen. So what we're going to do is break down the key ideas from this paper into a super practical guide you can start using pretty much immediately.
Okay, so here's the plan. First, we're going to nail down the problem that, let's be honest, most of us are facing. Then we'll introduce the main solution, the Minimal Viable Genome, or MVG. After that, we'll walk through exactly how to evolve an agent using real evidence, cover the common traps and how to avoid them, and then we'll wrap up with a quick recap and what to do next. So what is this agent scaling problem we're talking about? Well, it's the fact that so many agents today are built on just one single massive prompt. And because of that, they're incredibly fragile. They're a nightmare to update, you have no real idea what your safety guarantees are, and when something goes wrong, good luck finding a forensic trail. They just don't scale. The whole solution here is to just stop thinking in terms of prompts and start thinking in terms of genomes. Yeah, like DNA. We treat the agent's instructions not as one big blob of text, but as a set of distinct, heritable, modular traits. And that brings us to the core concept, the Minimal Viable Genome, or MVG. Think of it as the absolute smallest, safest set of instructions, or genes, that you need to ship an agent that actually does something useful. But here's the crucial part. It's designed to be the starting point, not the final product.
So what actually goes into an MVG? Well, you can think of it as a checklist. First, you need your immutable prime directives. These are the hard-coded safety rules that can never, ever be changed. Then, you define the core genes that give the agent its purpose, its identity, mission, tools. And this is critical. You must have a QA checklist gene, a metadata gene for versioning, and key resilience genes for that defense-in-depth security.
Okay, so you've shipped your MVG. It's out there, doing its thing. Now what? How do you make it better? This is where we stop just guessing and tweaking prompts based on a gut feeling, and we move into a really disciplined, evidence-based process.
Let's make this real with a quick scenario. Imagine we've built a policy summarizer agent. It's got a solid MVG, but our monitoring or telemetry is telling us it's just not hitting its performance targets. And we have the data to prove it. The numbers don't lie. The agent's citation accuracy is stuck at 75%, but its KPI, its target, is over 95%. See, this isn't some vague user complaint. This is cold, hard evidence telling us something needs to change. So we follow what's called the add by evidence flow. It's a simple process. 1. We review that evidence, the 75% KPI. 2. We isolate the specific need. Looks like it's a problem with formatting citations. 3. We propose a specific gene mutation. Maybe we modify the toolset gene to add a better formatting tool. 4. We test the heck out of it against our benchmarks. And 5. Only if it passes do we promote the change and keep an eye on that KPI. No guesswork anywhere. And a change like this really highlights an important split in the agent's DNA, the difference between core and resilience genes. Core genes define what the agent does, its identity, its mission, but resilience genes define how it does it safely. Genes like immune, which acts like a firewall, or repair, which can do automatic rollbacks, and lineage, which gives us that all-important forensic trail. All right, so now let's talk about hardening this whole system. We're going to look at some of the most common pitfalls teams run into when they try to scale their agents, and of course, how to fix them.
First up, gene bloat. We've all seen this in software, right? It's that temptation to over-engineer from the start, creating dozens of tiny, complex, untestable genes. The fix is so simple. Just start with that lean MVG. Only add new genes when the evidence, like a failing KPI, forces your hand. Keep it lean.
Next up, overlapping responsibilities. This is when you have multiple genes all trying to do basically the same thing, and they start causing conflicts and weird bugs. The fix here is to be super disciplined. Use the objective section of each gene to define its exact testable duties.
Make sure every piece of DNA has a unique job. Oh, and this one is absolutely critical. Untested interfaces. If your agent's tools can just accept or return any old data without validation, you have a massive security hole. The fix is to enforce strict contracts. Use a context contract to define exactly what the agent can see and do, and a sanctioned action schema to validate every single output before it's acted on. This creates a secure, predictable boundary. So where do you find all this evidence to drive the evolution? It's all over the place. You've got your formal red teaming and benchmark results. You have telemetry, like how often that immune gene is blocking bad inputs. You have incident logs from the repair gene's rollbacks. And of course, you have your basic run logs and direct feedback from your users.
Okay, that was a lot, I know. Let's pull it all together now and just recap the path to building these much smarter, much more scalable agents.
So, if you walk away with anything, remember these 4 things. 1. Always start with a minimal viable genome. Ship safe value fast. 2. Evolve your agent based on hard evidence, not your gut. 3. Proactively defend against common risks like gene bloat by defining clear responsibilities. And 4. Use those resilience genes to build in layers of security, a real defense-in-depth posture.
So what's next? If you want to take the next step, the place to really focus your energy is on those contracts and schemas, getting really good at precisely defining what your agent is allowed to see and what actions it's allowed to take. That is the absolute key to building truly robust and secure systems.
So I'll just leave you with this question to think about. If your agent's core logic today is just one giant, unstructured prompt, what kind of mutations are already happening in there without a version history, without any tests, and maybe without you even knowing about them?